Hi everyone, welcome back. That's the second seminar of our relaunch or new one-word API, so one-word approximate Bayesian inference. And it's my pleasure having here Jeremias Knoblauch, who is an associate professor and EPSRC fellow at UCL in the Stats and Machine Learning department, who will talk about post-Bayesian machine learning.
All right, cool. So thanks very much for hosting me. I just said to Marcy, but in case anyone didn't hear, I'm very happy to take questions during the talk. So I can't see you, however, so you may just have to unmute yourself and barge in. What this talk is titled is Post-Bayesian Machine Learning, and the reason for this is that I feel the title summarizes a lot of the work that we've been getting up to over the past years in the community that I'm part of. And specifically, these efforts have revolved around obtaining inference procedures that retain certain Bayesian or Bayes-like characteristics, while at the same time going beyond the confines of what Bayesian epistemology would really prescribe if you took it literally. And so just as a short preamble, I'm obviously not going to contest the validity of Bayes' theorem as a mathematical truth, but what I will sort of spend a lot of time thinking about during this talk is the translation of Bayes' theorem into an epistemological principle or a device for learning from data, because that translation requires that you specify a model on the data, and it requires that you specify a prior probability over the parameters of that model. And as we'll see, that can lead to some problems in the context of Bayesian machine learning explicitly. Why do we care doing Bayesian machine learning? People in the machine learning community will often tell you the things they care most about is averaging over models rather than picking a singular one. And they do so because they hope that it improves your predictions and because they hope they get some degree of uncertainty quantification about which parameter best describes your data. And obviously, they also care about prior expertise being incorporated into the model, even though they will pitch you that in the abstract. But when it actually comes to designing an inference procedure, you will often see that this is there's actually very little domain expertise going into a lot of machine learning procedures. Anyways, when you put all this together, as a simple example, one of the success stories of Bayesian machine learning, I would say, is the Gaussian process regression task, where you learn about some kind of latent function with a non-parametric Bayesian prior, and it sort of encapsulates everything that's good about Bayesian machine learning. So, okay, so this is why you would want to care about Bayesian machine learning in the context of, well, I should say, this is why you might care about Bayesian inference in the context of machine learning. But most of today, I'll spend on a second thing, which is lining out what sort of drawbacks you get into once you start applying Bayes' rule in the context of machine learning. And I'll show why this leads to certain forms of unreliability and a lack of robustness. And then the last part of the talks, I'll explain one possible fix, which I will summarize as post-Bayesian machine learning, which really just describes a very loose collection of algorithms that try to retain certain Bayesian characteristics without using Bayes' rule explicitly. And so obviously with the audience I have here, I could really get into the weeds of why Bayesian machine learning can cause some problems. I could really get into, you know, the foundations of Bayesian statistics that were laid in the 50s and 60s. But I feel like it's more advantageous to leave that perhaps for an informal chat or another day. And I'll just summarize some of the key takeaways of actually what are you assuming when you're doing Bayesian inference for that to be a good way of learning from data. And one of the key things you're assuming is that your model is well specified. And so basically, this is what I'll refer to throughout the talk as A1, assumption 1. And it essentially says that at least roughly your data should be able to be represented in terms of its sampling distribution by one of the members of your data model or your likelihood functions, so that there exists some theta star that can accurately represent the true sampling distribution. And the reason this is an interesting or important assumption is that it essentially allows you to limit your attention in how you learn from data. It allows you to limit that attention to the parameter space, right? So big theta here is the parameter space, and that's obviously the space you define your prior on. And the reason that it's valid to condense all your prior knowledge about the world or about the data generating process onto a prior belief about that parameter space is that that parameter space can represent the data generating mechanism in the first place. And so this leads to the second assumption, which is that actually you need to be able to specify your prior beliefs in a probabilistic way. So you need to be able to write down your beliefs about the world in a probability measure, which actually is very challenging in practice. And at the same time, that probability measure should reflect everything you know as it pertains to the data you're trying to model or learn about. And the third assumption, which I think is least contested, especially by this crowd, because it's something that people in approximate Bayesian inference have often thought about at great length and much more than I have, is that you can actually perform this inversion of probability, so that you can actually use the base posterior in practice, because you can at least approximate it to a degree that makes you happy that downstream decisions are based on that averaging. And that guarantees that Bayesian machine learning is actually practically relevant, because without that computation, you can't even begin to reason about its problems in the first place. And so what we'll see is that these three assumptions are quite fragile in the context of a lot of machine learning problems. And in order to explore this a bit more, what I'd like to do next is go through a sort of case study with a data set that comes from the late 70s. And that's actually very famous in the machine learning community. It's the Boston housing data set. So if any of you have ever read any machine learning paper that pertains to regression, I'm certain you will have seen an example being the Boston housing data set in a table where they check prediction error. But actually, the origin of this data set is in a very classic sort of statistical analysis framework where you're learning about data. And so I'm going to use this data set to contrast what we actually think of when we think of data analysis in statistics and Bayesian statistics. And I'll contrast that to what people actually think about when they think about Bayesian machine learning, and how those two things are separate. So in traditional statistical analysis, you will usually start with an expert that has a very well-defined research question. And then in an ideal world, at least, that expert approaches the statistician and is being helped in designing the model on the world that they want to learn about, and the way in which what is already known in the literature can be condensed into a prior. Right? So prior elicitation, mathematical modeling, these sort of tasks. And then once that job is done, all that remains to be done is really conducting inference. So you choose your favorite inference algorithm and you run things. And this is really the kind of setting where the Boston housing data set originally emerged in. So it comes from a paper by two economists from the late 70s. And their question was really, how does air pollution affect housing prices? And they have this really complicated, but in some ways simple model, but in some ways complicated in that you need to account for lots of factors, and is actually motivated directly from economic theory. So in some sense, you can say this is a well-specified model, not necessarily that it's a perfect depiction of the truth, but people have worked very carefully through what the model actually represents and have tried to match that very closely to reality. All of the parameters have a clear interpretation. And so it's actually easy to put priors on that kind of model, because the parameters in the model, they have clear meanings, and you could extract what people already knew in the literature and put that in some form of probabilistic distribution in order to learn about what the new data actually teaches you about these parameters. And actually, it's easy to compute any resulting posterior from this, because as you can see, the model we're dealing with is actually linear in the first place. So if you wanted to, you could probably work with conjugacy to get this in a closed form. So computation is really an afterthought in this example. And indeed, if you read this original paper, most of the paper is spent very carefully outlining how you should set up the model and so on. This is very different from how people learn from data in Bayesian machine learning. In Bayesian machine learning, people start with the model. So they don't start with a research question. They start with a flexible, often over-parameterized model. They throw that model at lots of different data sets and try to learn from that. And as a consequence of that, actually inference becomes a much more complicated task, because you've set up a flexible model. And the price you pay for that is that you can often not even compute it exactly. You often also care much less about the parameters of that model. You care much more about predictions. And so one example of where this is done, I could have picked amongst a million, but I picked this paper from 2020, where the research question of the paper really doesn't relate to any particular data set or any particular phenomenon. It really relates generically to the algorithm or the model that was posited in the first place. And so the research question is essentially, does this algorithm that we're suggesting here improve prediction on regression tasks, such as the Boston UCI dataset? And so the model that these authors use is a Bayesian neural network. And so, the underlying model, you could argue, is probably well specified in the sense that there exists a parameter that can recover something that's close to the truth. The prior, however, becomes really difficult to specify, because none of the parameters in this over-parameterized model are actually interpretable. So what they actually end up doing is they just put standard Gaussian priors on everything, which doesn't contain any information whatsoever, and crucially happens before you see any data. So the prior here really doesn't tell you what it should tell you in the standard Bayesian sense. And the posterior you compute, in spite of having compromised the prior, needs further approximation, right? So you already set up the prior in part so that you can even begin to approximate the posterior, but even so, the approximation is a million miles away from the exact base posterior that you would have obtained with the prior that is already compromised. So in other words, we have a set of assumptions that can describe one type of data analysis fairly well, and I think that's the kind of data analysis that we all grew up with, or that we were lectured to when we were younger, and it's an idealized world in that sense as well. But in that idealized world, those assumptions make sense. And then there's a second space emerged over the last 10, 20 years, which is how you can apply Bayes rule in machine learning, where really the assumptions that we've applied in Bayesian analysis, they don't make a lot of sense. And so I think this has been widely recognized in the literature over the last decade or so. And people have started trying to retain some of the benefits of Bayesian machine learning without having to rely too much on these three assumptions. And that has resulted in a body of work that I summarize as post-Bayesian machine learning in today's talk. And so the way that I like to conceive of post-Bayesian machine learning is really as a possible space of belief updates. So if you think about the base posterior, it gives you one algorithmic recipe really for learning from data given some kind of prior distribution. Now, when I say what a belief update is, I should be clearer here. Belief update for me, and this is very sketched, of course, there's no formality here. This is more for conceptually understanding what I'm talking about. Belief update just means you have some kind of mapping, which takes a prior belief over some space of interest, a set of data points, and maps that back into the space from which your prior came. Right? So posterior and prior obviously should be on the same space. And so in recognition of the fact that perhaps the base posterior isn't able to do things well in the context of Bayesian machine learning, people started experimenting with exploring the space of belief updates a bit more widely. And the simplest modification that you can apply is what's often called the power posterior, or the cold posterior, or the fractional posterior. It has lots of names, but it's a very simple recipe. You take the likelihood and you raise it to a power. So the idea here is that if your model should be misspecified, you can temper the likelihood and thereby actually make it into something that need no longer be a likelihood. And so therefore breaking Bayes rule, because when you multiply things together and you arrive at this power posterior, note that doesn't follow Bayes rule anymore. Right? Like if I take a likelihood, I raise it to a power, and then I integrate over the data space, that no longer needs to be equal to 1. In fact, it need not integrate whatsoever. So we have this new algorithmic recipe, which here I credit to Peter Grunwald, but he's not the first person to have this idea, but I think he started really pitching this idea as a way for learning from data. Okay, obviously one of the problems with the power posterior is that you now only have a scalar parameter to adjust the way you learn from data, and that's fairly restrictive. So what people started doing relatively soon afterwards is they said, we want something that gives us a bit more power, a bit more juice for expanding the space of belief updates we want to explore. And so instead of considering a likelihood, you can actually just use a different mechanism for coupling data to a parameter that you want to learn about. And one of those mechanisms is obviously a loss function. And if you exponentiate negative loss function, you can think of this as a quasi-likelihood. I don't personally like that term because, again, it's not a likelihood. If you integrate over x, it's not integrable necessarily. But it is a different way of updating your beliefs, and it results in something that's sometimes called the Gibbs posterior, sometimes called the generalized posterior, sometimes called the pseudo posterior, quasi posterior. I've seen lots of names for this, but the object that you're really looking at is the one in the green box here. And here I'm crediting this to Basiri, Holmes, and Walker. Again, they didn't invent Gibbs posteriors necessarily, but I think they really advocated quite strongly for their use for learning from data in their JSSB paper in 2016. And so with this, you can, reinforce the concern about model misspecification, and you can address this quite nicely through these objects, and we'll see some of that later in the presentation. And then the last sort of generalization of Bayesian principles that we'll consider in today's talk. There are others that I'm not going to consider, for example, the martingale posterior, which is really interesting, but we won't have time to cover that today. The last generalization we'll look at is one that takes the Gibbs posterior idea and generalizes it further, and it does so by considering the Gibbs posterior as one instantiation of a variational problem, and a fairly broad variational problem, which also recovers variational approximations that are common in variational Bayes, and really treats Bayesian inference as a algorithmic, or I should say post-Bayesian inference as a algorithmic recipe whereby you trade off a data fitting term with a regularization term, and that regularization is over the space of posteriors with respect to the prior. So one term tries to make sure that you are actually explaining your data. The other term is trying to stop you from deviating too far from your prior. And so this is the entire tapestry of belief updates we will consider in today's talk. The way that I want to structure this is in 3 parts. So in the first part, I'll go over what I would call foundations. So foundations really are the concerns that this literature emerged from, and those concerns revolve a lot around model misspecification. But what we'll see is that actually when you care too much about model misspecification, or if you care about model misspecification without respecting other properties of your problem, you run into the problem of obtaining post-Bayesian methods that are no longer computationally attractive. And so that leads me to what I consider the state of the art, which is a form of Gibbs measure, which is robust to model misspecification, but is also computationally attractive. And then in the last part, I'll give like a brief glimpse of what I think we can tackle or should tackle next. And this relates to more complicated problems where we now also worry much more about the priors being misspecified, where we worry about what we actually want to do with our posterior downstream, because often in Bayesian machine learning, people do not really care about parameter uncertainty other than for prediction. So I'll briefly talk about prediction-centric uncertainties as well. And so I won't mention my collaborators throughout the rest of the talk much, because I find it distraction when there's like faces everywhere. But this is not a one-man show, and it's not a one-man effort. Lots of people have been involved in this line of work. And so some of the people I've worked with, again, I can't even fit all of them on the slide, but some of them you can see here. So these are the heroes that have made a lot of this work possible with me. Throughout the talk, I'll kind of show you which assumptions are currently being tackled in the top left corner of the slide. And the top right corner of the slide will show you which part of the talk we're currently traversing. So if you need to leave and you come back and you're worried about getting lost, that should help you navigate through this structure. Okay, so the first part, we're basically addressing 3 questions, but the first of these I will address really briefly because I don't have as much time as I would like. So one of the first questions that we actually asked very recently in a rigorous way is whether tuning that lambda parameter in the power posterior can help you improve the robustness of your predictions. The second question we'll look at is what kind of losses will lead to Gibbs measures that give a form of robustness you should care about. And then lastly, we'll look at how you actually choose these losses in the Gibbs posterior. But yet, like I said, the first question, I'll very quickly skip over most of this. The important takeaway message here is if you just scale your posterior with some kind of power, what basically ends up happening really quickly is that if you think about what the lambda parameter is doing, it's really interpolating between the prior predictive and the plugin predictive. And the base posterior predictive has a particular role. It happens where lambda equals 1. And if Bayes were optimal in some sense, you would hope that actually the posterior, I mean to say posterior, if the base posterior predictive is predictively optimal, what you would hope to see is that this curve I'm showing you here would have a unique minimum at the base posterior predictive. This is kind of unsurprising that this happens, but this is actually not the case. What you find is that you benefit up to a point from learning from the data, and then it doesn't really make any difference anymore, whether you learn from the plugin predictive, the base posterior predictive, or something that has a value of lambda that's actually smaller than 1. Okay, so what this basically tells you, and this is why it's interesting here, is if you care about prediction, which people often do in Bayesian machine learning, at the expense of parameter uncertainty, this lambda parameter cannot save you. This is probably not very surprising if you look at the problem in a bit more detail, but unless you're in a very small data regime, just giving the prior more weight cannot really rescue you. And so what this leads us to conclude is that if we care about robustness of our predictions, we really need to focus on Gibbs measures much more. And so that's what I'll talk about next. So for Gibbs measures, what you need to do first is kind of think about what sort of robustness you actually want, and then how you could get losses that satisfy that kind of robustness. And that's a question we're going to look at next. When I say robustness here, I'm talking about Huber robustness. So just as a quick recap, Q epsilon here is the distribution from which you observe your data points. And Q epsilon consists in 2 parts, consists in some contaminant, So that's the red distribution here. That could be, some sort of outlier generating distribution, and a component which you can actually explain well with your model. So that's Q0, that's the yellow part. And just to give like a brief illustration of why this is a problem. So let's say this Q epsilon generated the blue histogram that we see here. And a part of that histogram was generated by some contaminating distribution circled in red. What now happens if you fit a Bayesian model to the entire data set, and that Bayesian model belongs to the yellow model class. So it could fit the first hump of the data well, but it can't fit a bimodal distribution. What basically happens is you oversmooth to the contaminants. And so this is the kind of behavior we want to avoid. And instead, we would want to actually fit the part of the data generating distribution that we can explain well. And informally, what this means is you basically want that whether you sample your data from Q epsilon or from Q0, that the posterior inferences you draw are roughly the same. So roughly speaking, this is going to be what we want. To formalize this a little bit, what this means is you need some kind of distance measure between posteriors, and you need to make sure that the distance between posterior measures is bounded as a linear function of epsilon. Okay, so as you increase the amount of contamination, you basically want that the divergence between the posterior inferences from the contaminated and uncontaminated version only scale as a function of, like, as a linear function of epsilon. This is sort of, that's an ancient desiderata from the robustness literature. I'm not going to go into why you want this. But if you just guaranteed the statement that I wrote on the slide now, without worrying about what that distance actually is for now, actually you could cheat, because you can pick a sequence of contaminants that make the right-hand side arbitrarily big. So obviously we don't want that. So instead, what we want is we want to actually bound the worst possible contamination linearly in the size of that contamination. So we take a supremum over all possible contaminants. And now I still haven't spoken about what kind of distance you would want to choose. And actually, I think in some ways, the choice of distance for me is still an open question. But the one that we work with for the time being, mostly because it's convenient, is the supremum distance. So that means you look at the contaminated, the uncontaminated posterior across the entire range of theta, and you look at the difference in the density between the two, and you pick the worst possible case. Why is this convenient? The reason this is convenient is it allows you to express the robustness completely in terms of a property of the loss function. And in particular, it allows you to think about the robustness of the Gibbs measure entirely in terms of the loss sensitivity to contamination. Why is this interesting? That's interesting because the original distance was defined on the space of probability measures, nasty space to deal with, complicated, not easy to analyze. And now we've simplified this into a quantity that lives on the Euclidean space. And actually, the key quantity really that you should look at here is the limit of this loss sensitivity as epsilon goes to 0. And that's essentially just the derivative of the loss that indexes your Gibbs measure. And it's the derivative of the loss relative to the size of the contamination evaluated at 0, which means you're now looking at how the loss behaves for an infinitesimally small contaminant. And we'll call a loss robust in this sense whenever that sensitivity, irrespective of theta, is upper bounded. And what you can essentially show is that the posterior that you obtain, or the Gibbs measure you obtain, is robust whenever the loss is robust. And so that's a really nice finding that we've worked with as a way of, determining which losses lead to robust posteriors. One quick note, this is probably too coarse. So probably what happens here is the requirement on the loss is probably too strict. You can probably get away with milder requirements on the loss to get a stronger robustness theorem, but that comes at the expense of a lot of technical investigation, and then it becomes really difficult to verify that your loss actually satisfy this property. So for the time being, this is a useful guiding tool, but I think in the future we'll have to improve this. Okay, so in principle, this is how we can find a loss that's robust, but I haven't actually spoken about what these, where these losses should come from. What should we replace the negative log likelihood with? And so to do that, it makes sense to go back to some of the work that Jack Jewson did in 2018, 2019. And in particular, what Jack realized is basically when you look at the loss function from standard Bayes, it's assuming that the data is IID for the time being because it simplifies our problem. If we assume that the data is AID or at least exchangeable, then we can actually think of the negative log likelihood as an approximation to the KL distance between your true data generating measure and the model. And we know that the KL distance is not robust. So conversely, if we construct a discrepancy that is robust, then if we can construct a loss from that robust discrepancy, it should follow that we actually get the form of robust loss that we should want to construct Gibbs measures. And this is exactly the kind of work that Jack and I did in the late 2010s. And so some of the things we looked at were beta and gamma divergences. Both of these are losses that are indexed by a hyperparameter beta and gamma. And as that hyperparameter approaches 0, you revert to the negative log likelihood. So this has the effect of basically giving you a base posterior that behaves, sorry, not a base posterior, a Gibbs measure that behaves like a base posterior, but after you've removed very severe outliers. But crucially, you don't have to remove the outliers by hand. So the benefit of this is that the uncertainty quantification you obtain is very, very similar to something that you would get from Bayesian inference. So it retains all these nice interpretations, but it excludes the outliers for you without you having to worry about them explicitly. And this is very nice in high-dimensional problems where you don't necessarily have the ability to identify an outlier with simple scanning methods. And so we took these ideas and we applied them to some Bayesian machine learning problems. So for example, the deep Gaussian process. This work was published in 2022, but we redid this in 2018, 2019. And what basically happens in deep Gaussian processes is you have a hierarchical construction of Gaussian processes, which becomes computationally extremely involved. And so the hidden layers here are just the number of Gaussian processes that you stack. And the fewer of these you stack, the more computationally tractable this actually becomes to do inference with. And what we found is that when you make your losses robust here, so if you compute a post-Bayesian posterior, which allows for model misspecification, you're essentially saving yourself the computational equivalent of one hidden layer. So that means that in terms of computation time, the payoff of a simple modification, because there's really like 1 or 2 lines in the code you need to change, is quite substantive. So you can see here, for example, with one hidden layer, the robust deep Gaussian process is as performative as the standard deep Gaussian process with 2 layers, and that sort of continues that trend. Okay, so if you know gamma and beta divergences are such great losses, why don't we see people use them all over the place? Actually, there's a very simple explanation for this, and the explanation lies in the fact that I haven't shown you what the loss looks like. Because if you actually look at the loss, it is essentially an integral over your model class. And that means that in general, you need to approximate it with samples. And that's really unattractive for obvious reasons. The deep Gaussian process example I showed you on the previous slide is sort of exempt from this, because whenever you have certain exponential families of which the Gaussian is a member, you actually obtain these integrals in closed form. And so therefore, you don't have this problem. But for general likelihoods or for general models, this is a huge problem. In fact, we studied this fairly recently with David Fraser and Chris Randi, and we looked at how many samples would actually be required for us to approximate these Gibbs measures to arbitrary precision. And the answer is basically it's terrible. So you see here, this dotted black line is the exact posterior that you would want. S is the number of samples that you draw from the model to approximate this intractable integral. And even if you take 100 times as many samples from the model as you have observations, you're still nowhere close to the Gibbs measure. And we managed to actually quantify the order of samples that you need in order to retain a constant approximation quality. And it basically turns out that for gamma and beta divergences, that it needs to be at least quadratic. So you cannot really do this in a computationally feasible way, especially in high dimensional and big problems where you would want this stuff in particular. So this leaves us at a somewhat, bad place after the first part, right? So we talked about robustness. We saw when we can prove robustness, that was nice. Then we spoke about how we should choose robust losses. And we saw actually the moment we do this, we introduce a trade-off between robustness and tractability. And it's that trade-off that I'm going to address in the second part of the talk, where I'll talk about how we've come up with methods now that can deal with model misspecification while at the same time retaining computational feasibility. And really, when we started this work, we were inspired by what people do in the context of unnormalized likelihood models. So in an unnormalized likelihood model, you have some sort of density nu. The nu here is a valid density, but it's not a probability density. So you need some kind of normalizing constant z theta in order to make it a probability density, but that z theta is not available to you in closed form. So again, it's intractable. The sort of naive solution to the problem is the exact same solution that we saw with the beta and gamma divergences. You can just sample from that density and approximate your normalization constant with a sum. That's terrible in so many ways that we're not going to go into that. Instead, what we were thinking of doing is there is this one loss function that people use for this problem that is actually really elegant and completely circumnavigates this intractability problem, and that's score matching, or more broadly speaking, Stein discrepancies. And those were the losses that we actually found can give us robustness and tractability. So as a brief reminder of what score matching actually does, so we have the setting where we have a likelihood with an unnormalized constant. Sorry, we have an unnormalized likelihood, intractable normalized, I should say. What you can do, assuming that the density that you do have access to is log differentiable, is you can evaluate the gradient with respect to the data of the log density. And that turns out to be really nice because through some simple algebra, you can show that this is exactly equivalent to taking the gradient with respect to x of the log likelihood of the model. And that last term, so the gradient of the log likelihood with respect to the data, that is called the Stein or Hiver-Reenen score, because assuming that you can evaluate this, you can define a sort of loss function that looks at the difference between that object on the model and that object on the data generating density. And you can kind of show that if you minimize this, your model will actually be close to your data generating density. Only problem here is obviously the data generating density is not something we have access to, but fortunately integration by parts and approximation through an empirical measure come to our help. And then you can basically show that score matching can be rewritten in terms only of the Stein scores of the model. So this is now something you can evaluate, assuming that the first two derivatives of the log density, and I mean the unnormalized density, are something that you have access to. And now you've ended up with a loss function that no longer suffers this intractability problem. Okay, but we're now we have a problem, right? Because so now we have this score matching loss, which is great because it's tractable, but we actually can show that score matching is essentially minimizing the Fisher divergence, and the Fisher divergence is not a robust divergence. So I've given you all this pitch at the beginning of how we can address model misspecification, and now we've ended up with a divergence which doesn't actually give us robustness. Fortunately, this is quite an easy fix. We can basically see the Fisher divergence as a special case of Stein discrepancies, and once we make that step, we can choose Stein discrepancies which generalize the Fisher divergence in a way as to make it robust to misspecification. And from that, you can essentially derive losses that amount to a generalized version of score matching, which are both robust and tractable. And really, the recipe for doing this are essentially Stein discrepancies. So there's a very simplified presentation of Stein discrepancies here, but I kind of want people who haven't been exposed to them previously to take away the main reason why they're interesting in the setting. So Stein discrepancy essentially looks at the difference between two probability distributions by considering the difference in expectation over a set of test functions. And that set of test functions here is indexed by calligraphy f theta. Now, it depends on theta, because one of the things we will immediately do with Stein discrepancies is we will choose that set so that one of these expectations is something we never have to worry about. Okay, so automatically one of them is 0, which simplifies the intractability of this distance quite considerably. And then we do a second smart thing in the design of this calligraphy f theta, namely we design it so that this supremum over a expectation can be rewritten in terms of an expectation over a function f star to which we have access, okay? And that makes our life really easy because now we just have to evaluate an expectation over some kind of function. Well, we can approximate that with samples from the data generating distribution. And that gives us access to a loss that we can evaluate. And importantly, the functions f that we allow to be in calligraphy f theta are now allowed to depend on theta itself only through two terms, namely the score, the Stein score that we discussed earlier, so that we know is tractable, and the weight function. And the weight function is what gives us robustness, and the Stein score ensures that we can actually evaluate this and make it tractable. And so that way we arrive at something that, provided that a density has, that the log of a density has two derivatives, can be evaluated and is robust if we design our weight function carefully. Let's compare this to the base posterior. Okay, so the weight function ensures it's robust, and we know that the base posterior isn't. So that's a win for us. If we look at intractable likelihoods, we know that the Stein discrepancy-based posteriors actually are going to be much faster to compute than the base posteriors, because you no longer have to deal with doubly intractable likelihood problems here. If the likelihood is tractable in the sense that you don't have this problem with a normalization constant that's unknown to you, they will be roughly as fast, and you can even use the same kind of algorithms. You can use standard Markov chain Monte Carlo methods or whatever favorite choice of computational hardware, software that you want to use. So the only setting in which we should be worried about the base posterior being computationally more attractive than the Stein discrepancy is the case of conjugacy. So if you have an exponential family and a conjugate prior, you would expect that the base posterior is quicker to compute. But actually, this turned out not to be the case. And the reason for this is that conveniently, the Stein discrepancies with respect to exponential families always turn out to be a quadratic loss. And that's nice because when you take the exponential of a negative quadratic loss, it looks suspiciously similar to a Gaussian because it kind of is. So you have a squared exponential quasi-likelihood, and you can make that into a conjugate posterior by putting a prior on theta that is also squared exponential, in other words, Gaussian or truncated Gaussian. And this actually allows you to obtain one of those Gibbs measures in closed form. And crucially, this happens even if the original likelihood model you started with has an intractable normalization constant. So in other words, your Stein discrepancy posterior has a closed form for exponential families and Gaussian or squared exponential priors. And that means that it's as fast or faster than base posteriors in the setting. The faster here comes from the special case where you have an exponential family that is actually intractable, which happens for certain graphical models. And so we've exploited this property quite widely in a range of different applications recently. And one of the really nice applications for this is actually closed form updating in online problems. So for example, we have a recent paper on Kalman filtering, where strictly speaking, the updates used here are not Stein discrepancies. They're a form of weighted likelihoods, but you can do the same with Stein discrepancies and the results are very similar. But what you basically find is if you run a Kalman filter and you have a lot of outliers in your data generating distribution, obviously a standard Kalman filter is not going to work well. If you use one that's been robustified and is a generalized Bayesian procedure, you do still manage to track the latent function really well. And obviously there's lots of other robust Kalman filtering ideas out there, but what makes this one special is that you actually update things exactly. So there's no approximation anywhere. You are no longer targeting a sort of standard Bayesian version of your posterior over the latent function, but you are targeting exactly, and you're obtaining exactly inferences, post-Bayesian inferences about a latent function that are robust. So there's no approximation error involved anywhere. The updates are exact and in closed form. Okay, so this ends the second part of the talk, right? So we saw that we can actually design losses that are robust and tractable. You can do this via Stein discrepancies and weighted likelihoods, which is the Kalman filter example I just showed you. But it's sort of not enough to really make Bayesianism attractive for a lot of the problems that people care about in machine learning. And so the last part, I'm going to look at some of those aspects. So that relates to if you really care about prediction more than anything else, if your priors are really poor or shouldn't really be thought of as priors in the first place, and lots of other challenges. And so the three questions I want to touch upon, if I have the time, I'll probably try to end in like 7-ish minutes or so that we have some time for discussion at the end. But some of the questions that I want to quickly discuss in this part of the talk is, how would you actually go about designing a posterior that should be robust to the prior? How would you design a posterior that is better or that is geared towards prediction rather than parameter inference? And how do we actually compute these posteriors once we really go whole hog? And so for that, it's kind of important for us to go back to this optimization-centric view on the base posterior and really understand this is originally motivated by Gibbs measures and by recovering Gibbs measures as an optimization problem and then generalizing the components of that problem, right? So I can take a loss which couples my data to the likelihood, my data to the model, and I can generalize that. And we've seen in the talk so far how that has led us to improved computation and actually models that are better specified. sorry, not models that are better specified, but robustness against misspecified models. We can similarly play with the regularization term to change the way we regularize against the prior. And we can obviously, and this is something people do in variational inference, play with the set of measures over which we solve this variational problem. Okay, so for the question of how we can address bad priors, it's fairly obvious which component of this problem we should address this through. And that's obviously the regularization term. Okay, so it's much easier to think of this in terms of the dual problem or the Lagrangian of this problem. You can think of this Qn star that I've written out here as an objective function that looks at minimizing this green loss between a posterior and the data, subject to the posterior being in a delta ball around the prior. And so a lot of these robustness concerns about your prior will boil down to the structure or the geometry of this delta ball. To sort of illustrate this a little bit, you can think of a ball which, this is purely conceptual, like this is not hard maths, but you can think of this ball as living in a two-dimensional space. One axis is the difference in mean between prior and posterior. The other axis is the difference in entropy. Now, the origin here is the point where Q equals pi. So this ball is not symmetric around the origin. It's symmetric around the y-axis, but not the x-axis. And that's important because basically what this tells you is for this specific geometry, it would be easy for the posterior to deviate from the prior in terms of mean in both directions. But it would be also easy for the posterior to be more entropic than the prior. In other words, to be less certain about which parameters best describe the data that have been seen. But conversely, it would be hard for the posterior to concentrate more than the prior. Okay, so it would embed a form of conservatism into the posterior that's often desirable when you work with these sort of black box Bayesian machine learning problems, like let's say a Bayesian neural network. Okay, so this is basically what we often want in black box machine learning priors, because really our prior is not a Bayesian prior anymore, it's just a reference measure. But instead, what people do is they regularize with the quadratic-Leibler divergence. And actually what that looks like is a lot more like this. So in other words, it's way too easy for the posterior to actually contract more than the prior, which is something that people will often refer to as a mode-seeking behavior of the quadratic-Leibler divergence. And so to sort of explore this briefly on an example, this is a paper by Veit Wild. You can forget the top part of this panel. I think just focus on the 1D projection. Basically, you have some sort of uncertainty in the predictive space here. You're fitting a Bayesian neural network to that with HMC. So, it's probably as good as it's going to get in terms of the Bayesian uncertainty quantification you get out of it. And you can see there's some degree of uncertainty quantification around the space where you don't observe data. So the red point clouds here are where the data actually lies, and you can see the space in between. There's not a lot of uncertainty there, like it collapses fairly quickly. And that's simply due to the fact that you regularize with the quadratic-Leibler divergence. So your posterior is prone to collapsing. This is even more severely true if you start approximating the space posterior, right? I mean, the notion of uncertainty quantification you get here is not useful for anything. But actually, once you start playing with the regularization term, you can really change things. So you can make this a much more conservative form of uncertainty quantification. So in this instance, you regularize with the Wasserstein distance. And this is purely empirical. Like there's no thorough explanation that we have. I want to stress this. There's no thorough explanation that we have why exactly this happens, but it will relate to the geometry you induce with different regularizers. There's a different question altogether, which relates to prediction, right? So often, and I said this throughout the talk, you may not even care about parameter uncertainty if you're working in Bayesian machine learning. You just care about the fact that averaging of your model improves your predictive performance. And that can be a problem, particularly in deterministic models. So for example, here we have a Lotka-Volterra model. In the Lotka-Volterra model, you don't actually account for measurement error. It's a purely deterministic error. So you can kind of ignore this and inject like a minimal amount of noise, and then you can perform Bayesian inference, which is what we've done here. And what you see is that out of sample, so the circles and the triangles here show you where the data actually occurred, and the lines, the dashed and solid lines, show you where the true data where you predict the true data to arise, whereas the gray lines show you where actually the true process is happening. What you can see is that your predictions are way off, but you're also completely certain about them because this is a deterministic model. You might think, okay, great. This happens, by the way, because the model is misspecified. So you might think, okay, great. It's just because the model is misspecified. Surely, if I use, one of these robust posteriors that we were talking about earlier, I can fix this problem. That's actually not the case. So if I use, in this case, it's a maximum mean discrepancy based Gibbs posterior, you get exactly the same problem. And it's again for the exact same reason that your model is actually deterministic, but it happens to be wrong. So this leads to bad predictives because the predictive collapses, and that's sort of a feature of the model. It means that the intersection between the predictive and the truth is basically zero. And it doesn't matter whether you do your inferences robustly or not. This is always going to be the case. So in order to address this, one thing you can do is you can look at this loss function and actually construct it in a way where it's no longer averaging over the loss that you suffer for a particular choice of theta, which is the way that Gibbs measures think about this loss. Instead, let me skip over this real quick. What you can do is you can design the loss in a way where you are directly targeting the predictive distribution. So instead of thinking about the fit of the data, you're thinking of the fit of the predictive after you've averaged out over your likelihood model. And there's some previous work in this direction, and mostly it focuses on using the Kuiper-Gleib divergence as a measure of discrepancy for this. And that leads into all sorts of trouble because the KL basically depends on log integrals that you can't compute outside of very narrow niche situations where you get this enclosed form. And so very recently, Chris Oates, Sam Power, and one of Chris's postdocs and I, we got together and we derived a version of this problem where we look at a discrepancy that is the maximum mean discrepancy instead of the KL. And when you do this and you run the procedure, because you can actually sample from the resulting posterior exactly, which is kind of cute as well, what you end up with is something that produces much better predictive uncertainties because you have constructed it so as to do that, right? So this is no longer about quantifying the uncertainty about a parameter, which is what Bayes posteriors and Gibbs posteriors are about. This is about quantifying the uncertainty in the parameter as it pertains to the predictive. So it's what we called in the paper prediction-centric uncertainty. And I think that's one of the ways forward that are interesting to explore as well in this space. Okay, so in the last 3 or 4 minutes, I want to quickly talk about how you can actually compute these kind of optimization-centric objects from first principles, because obviously it's not easy. Once you start formulating things in terms of an optimization problem, they're no longer Gibbs posteriors, so you can't use Markov chain Monte Carlo, and there's not an analytic form available to you to exploit. So what people did previously is, they just said, okay, let's do what people do in variational inference. Let's put a parameterized family over that Q and minimize this objective over these finite dimensional parameters via gradient descent. And that works fine, but it very strongly, constrains the shape of the posterior that you can compute. So what we did more recently is we actually said, well, we could think about this objective as, this is an objective that is defined over the space of measures, and it's actually often convex over the space of measures. So can we do something that is like gradient descent on the space of measures? And actually the answer turns out to be, yes, you can. And the answer turns out to be Wasserstein gradient flow. So without going into any detail, you can basically implement in a range of settings the Wasserstein gradient flow directly on this objective. And then that allows you to obtain a sampling algorithm that can sample from this Q star n, even though you don't know what Q star n looks like. So you're basically performing infinite dimensional gradient descent. And one of the bonuses of doing this, it tells a little morality tale on which I want to end today's talk. Okay, so we have this very general purpose algorithm for sampling from posteriors that are defined through optimization problems. And one of the special cases is actually, unsurprisingly, the cold posterior or Bayes posterior. So if I minimize the objective that I put on the slide here, you end up, when I say optimize, when you apply Wasserstein gradient flow to this objective, you end up with the Langevin diffusion. The Langevin diffusion is a very well understood motor for a lot of sampling algorithms. And if you follow it, you know that the particles actually converge to a well-defined density, and that density is just the cold posterior or the Bayes posterior. If you take that parameter lambda all the way to infinity, so you're now completely ignoring any regularization and you just pay attention to what the data tells you, you end up with ensembles, right? Or what are often called deep ensembles in the context of neural networks. A deep ensemble is still a Wasserstein gradient flow, but it's a Wasserstein gradient flow on an unregularized objective. And unlike a Langevin diffusion, a Wasserstein gradient flow on an unregularized objective, unsurprisingly, is just gradient descent, basically. So it crashes into the nearest local minimum and it sticks there. It doesn't wiggle around or anything. It doesn't explore the space. So this means, A, it converges to a measure that's fully discrete, assuming that there are finitely many minima, or at least countably many. And B, it completely depends on where you initialize your gradient flow, which is very different from the Langevin diffusion, which does not depend on this initialization. So those two algorithms are completely different animals. They behave completely differently. They should not be thought of in the same way. But there's a persistent claim in the Bayesian machine learning literature that actually deep ensembles are Bayesian inference. I mean, this is not a correct claim in my opinion, and this is a problem. But in some ways, it's really good for the kind of work I want to do and for arguing why what I do matters, because what it shows us is two things. That first off, in practice, orthodox Bayesian machine learning has already been abandoned within the ML community, right? So we saw a base posterior that depends on a prior regularizer, and the prior needs to be something that you carefully think about. You think about things in terms of densities, and they're well defined. A deep ensemble doesn't even have a prior regularizer often, and you arrive at a fully discrete measure. Those two things are completely separated. And yet, as a field, we don't really have the right language for talking about these distinctions, because at the end of the day, what people want to do with deep ensembles is still fairly similar to what they want to do with a base posterior, at least in machine learning. I'm not saying that this is a good idea, you know, if you do biosciences or medical sciences, but in machine learning, the end goal with both methodologies is still very similar. And so because we don't have the right language for talking about the distinctions between a more orthodox Bayesian approach and other sort of measure valued estimators, we are making claims in that field that are just not correct, and that lead to conclusions that are misleading. And deep ensembles are Bayesian, for me, is one such conclusion. Okay, and with that, I want to end today. Sorry, I think we have only about 3 minutes left. Before we go to some questions, I wanted to also advertise that from mid-January onwards, we're going to organize fortnightly seminars on post-Bayesian research, so specifically pack Bayes, generalized Bayes, and martingale posteriors and resampling schemes. And there will also be a workshop at UCL on post-Bayesian methods in the middle of May that you can sign up for. You can either follow this QR code here, or you can just use this tiny URL link that I've supplied. Okay, there's also some references, and I think I'll stop here, and we can take some questions.